Okay, this is number 80 in the book. They ask us to find dx dp and then to find and interpret the value of that derivative when p is $10. So what they gave us here is sometimes called a demand function, and it relates the price of a product to the number of units demanded by consumers. Because usually when you change the price of something, the demand of that product changes. So X is the number of units consumers are going to demand, P is the price. And here X is written as a function of P. So clearly if you tell me a price, we can use this formula to figure out how many of units of that product are demanded. And usually what you find, the more expensive the product is, the higher the price, the fewer units will be demanded. And I think you'd see that with this function. But what they actually ask us to do is compute the derivative, dx dp, and interpret it at a specific value. So we'll think about what the derivative is, but first let's compute it and just get the formula. So if you look here, again, they give us x as a function of p, and they want dx dp. Okay, so dx dp is going to be the derivative with respect to p of the function, right? And we can use just regular old differentiation here because x is a function of p, and we're asked to find the derivative of x with respect to p. So I'll take the derivative of this formula with respect to p. Okay, you know, one thing that makes this a little bit different is that normally x is the independent variable of a function. Here x is the dependent variable. Okay, but the derivative we're asked to compute is dx dp. So if we have a function that depends on p, which we do here, you know, it's just a matter of switching the role of the letters. So it's really nothing. Whoops, there we go. Okay, nothing major going on with this one. The biggest difference is that the variable is p. Okay, so what do I do here? Well, this is a quotient, so probably we want to use the quotient rule. You know, remember in the quotient rule you've got a numerator and a denominator. Okay, we usually call the numerator f and the denominator g. The quotient rule says to find the derivative of a quotient, take the derivative of the numerator, okay, with respect to p in this case. Well, the derivative of 500 is easy, that's 0, okay, times the denominator, okay, which I really don't even need to write this down because we're going to multiply it by 0, okay, minus the numerator times the derivative of the denominator. Okay, so we're taking the derivative of natural log of p squared plus 1 with respect to p. Okay, so really what we're using is this rule. Okay, probably writing it a little bit different than you're used to, but you know, just to kind of compare it, it's the basic rule for differentiating log of a function. You know, the only thing that's different is that we're differentiating with respect to p. So I take the derivative of what's inside with respect to p, and that's just going to be 2p, okay, over the stuff inside. Okay, p squared plus 1. And this is all over the denominator squared. Okay, and when you square a log function or you raise a log function to a power, it's a good idea to put it in parentheses or a bracket. That tells me that it's the log function that's being squared, not the stuff inside. If you just put a 2 here, it would look like you're taking log of something squared. But here we're squaring the log function. So that's the way we want to write that. So what do we got here? dx dp, okay, the thing we're asked to find is, let's see, well, I can simplify things a little bit. I can write this as negative 1000 p over p squared plus 1 all over natural log of p squared plus 1, that whole thing squared. Okay, so again, it's a complex fraction, which we don't like, so I'll probably write it one more way here. Negative 1000 p over p squared plus 1, okay, and instead of dividing by, you know, the second term here, I have a fraction in the numerator. If I'm dividing by natural log p squared plus 1 squared, I can just multiply by 1 over that, which is just going to put this in the denominator. So in the denominator I should have natural log of p squared plus 1, okay, squared. Okay, so that's dx dp. Now, what is dx dp? Well, the great thing about derivatives is you can always interpret their meaning based on what the derivative is. We're taking the derivative I should say what we're differentiating. We're taking the derivative of x with respect to p. So we're looking at the rate of change of x, which is the quantity sold or demanded by consumers per unit of p, price. So you can interpret this as the change in demand per, so the change in number demanded, the units demanded, per change in price. And what do we mean by change in price? Well, we're talking about units of dollars, so we can say per dollar. Okay, change in demand per dollar. So what that means roughly is that if you put a number in for P, this derivative will give you the rate of change of demand per dollar. Okay, so again, we'll look at the rest of the question here and we can kind of interpret it. They ask us to compute dx dp when p is equal to 10. Sometimes we like to put this over to the side just to let us know we're computing a value of the derivative when the variable is a specific number. Okay. Well, basically all you have to do is type this into the calculator, and it takes a little bit of time. But when I do that, I got it over here. Actually, let me try it again here real quick. So all I'm doing is I'm putting that derivative into the calculator, but I'm changing p to 10 because we're asked to compute this when p is 10. So let's see what we get. I'm going to go ahead and do it again here. Okay, and so I get negative 4.65. Okay, so when the price is $10 per unit, demand is changing by decreasing about 4.6 units per dollar. So that would be the units actually. Negative 4.65 units per dollar. Okay, and again, the interpretation is when I'm pricing them at $10, you might ask, what's happening to demand per dollar we increase price? So roughly what's happening when we go from $10 to $11? And the answer is this. Demand is decreasing by about 4.6 units per dollar. Okay, so again, it's just sort of an instantaneous rate of change. Certainly when you sell, when the price is $11, you're going to sell some whole number of units fewer, but at least instantaneously at that moment, here's what's happening to demand. For every dollar we increase the price, we're losing about 4.5 to 5 units of sales.